Hey everybody, this is Devlog, I don't know, number 4 or 5. But in this video, I'm going to talk more about electricity and how pinball control systems actually work. I actually started, I think, officially, air quotes officially working on this pinball build back in December of 2024. Whenever you take on a really big multi-phase project, it's not always obvious where you should start. And so the very first thing that I did somewhere in the first half of 2025 is I built the backbox electronics. Now, I don't actually have the backbox built yet. So instead what I did is I just got a board that was slightly smaller than the backbox and I mounted everything to it, and then you can see I've got these handles in the left and right. And my idea was that there will be some like tabs, corner tabs that I will click this in and out of the back box. And so then I can take it out and work on it, or I can put it in the back box. But for this video, what I want to talk about is what I've got here, how this works, and I want to walk through the entire flow of how a coil actually fires in the fast system. So first of all, we're dealing with electricity. So we got to have electricity to run this thing. So we go from 120 volts AC to 12 volts DC and 48 volts DC. The 48 volt is what runs the coils, and the 12 volts is what runs the lights and all the boards. So you can see here, 120 in, and then 48 and 12 out. So here's where the 48 and 12 come in. So the 48 comes in here, the 12 comes in here, and both of them flow into this board here. This is the power filter board. And probably the most notable feature of this is these 3 mega capacitors. You can think of these as like huge water tanks. They store up electricity so that when a coil fires and it needs a massive inrush of current, they are there to provide that. All right, another big piece of this, and as you can see, there's a lot of text, is there's the PC that runs the game software. So this is actually being powered by power over USB. So the line starts here. So out of the power filter board, we've got 12 volts, and then it snakes under and it comes in over here. This particular board, this is a single board computer. This is the ARMSOM SIG 12. No, sorry, the ARMSOM SIG 7. I'll put a link in the comments. Anyways, you could think of this like a 5 times more powerful than a Raspberry Pi, but only cost about 30% more. I started with a Raspberry Pi 5, and you can definitely make a game work on a Raspberry Pi 5. You're going to have to be pretty lean on what you do. However, the SIG 7 just was a lot more powerful. Anyways, this is running Debian right now. And what the responsibility in the control system of the PC is, it's going to be the rules, so that's like your modes or what happens when you hit this or that switch. It's also going to be the thing that plays the sound effects and whatever video or animation or score display I ultimately decide on, it will manage that as well. So it has a handful of outputs. The 3 of interest are HDMI for a display, USB, which is going to go into this board, which I'll talk about next, and then, of course, 3.5 audio. That'll then go into an amplifier and power the speakers. I don't have any of that yet. All right, and then lastly, maybe the most exotic of the things on this board is the fast neutron. What the neutron does is it's the coordinator of the 3 communication buses that are part of the fast system. So those buses are the input-output, or the I/O network, the expansion bus, and the display bus. So you can see here this USB coming out of the PC goes into this board, and that's how all of this goes. So we've got power out, we've got power to run the PC, we've got control signals going into the neutron, and then we'll talk about what comes next. So let's say that we want to build a pinball game and we want to implement start game. So in order to do that, there's some different responsibilities. The first thing that we may want to do is reset the player score to 0. That's going to be a value in computer memory. That's going to be handled on the PC. The second thing that we would want to do is we would want to load a ball into the plunge lane. Now, in that case, the PC is going to need to tell the neutron, hey, fire this coil. Let's just say it's coil number 23. Fire coil number 23. It's going to tell the neutron. Now, what happens after this point, right? We know that something needs to take place here. Boop, boop, beep, boop. And then, electricity gets to an actual coil. But but what happens there? As I mentioned, the Neutron has 3 buses. The I/O, or input-output network, it primarily runs the drivers and the switches. Now, a driver, that's kind of a, I don't know, strange term maybe in the pinball world, but really what you can think of that as is a driver is a firmware-controlled MOSFET or like a electronically controlled gate for electricity. And anything that we have that needs an inrush of electricity, like a coil or a motor or whatever, can be attached to a driver. So the I/O network is really for things that either the player is interacting with or that we want to interact with the player with. The EXP, or expansion bus, runs things that are more so in the vein of where we're displaying something to the user. So this is like lights or servos. Technically, you could say a servo is interactive with the player, but usually most of the time those are more of a cosmetic type of feature. The Neutron also has a thing called the display bus, and it's not very well documented, and I'm not using it, so we're going to skip it. Anyways, the Neutron and the I/O network specifically, that along with the expansion bus will connect to the playfield. The playfield, of course, is the flat part of the game. And there's a couple ways you could do this. There's an optional board from Fast, which I am using, called the interchange board. And it's just an easy way that we can plug the Neutron into the playfield, and then anything on the playfield we can plug that into the interchange board. So after the interchange board, that then plugs into our I/O boards, or if I was using expansion boards, it would plug into those as well. I'm not there yet. And the I/O boards are what have the actual ports for switches and coils. So on this board here, these orange lines are for switches, and these gray lines are for coils. Now, one of the important things about the I/O network is that it is actually a loop. So as you add devices, all they do is they widen the loop. So the signal goes out of the Neutron into the first I/O board, and then out of the first I/O board into another I/O board, and then back into the Neutron, so it completes a loop. And that's how this network is able to both turn coils on as well as to know when a switch has been activated. So in order to get down to we actually want to fire a coil, of course, we need to connect it. And basically the way that this works is all of the coils, you can see over here the blue line, all of the coils will get 48 volts DC positive applied to them. You can see that's on the side of the flyback diode. And then the ground line will go into a specific port. You can see there's this kind of grid of squares here. Those are the MOSFETs. So that's actually what is electronically opening and closing this high current power. And so we can send instructions to this board to basically say this exact pin right here should have its gate opened, and that completes the circuit and causes the coil to fire. Drivers can run in 3 modes. So there's manual, and that's where the software tells it when to fire. There's automatic, you can give it some instructions and let it fire on its own, and then of course disabled if you're temporarily turning it off. So disabled would be, for example, when you're in attract mode and the user hasn't paid enough credits in order to play a game. Now, automatic mode is interesting because it works typically by binding 1 or more switches to the driver. So for example, we could say activate this driver when switch number 12 is closed. But as you think about that, activate this driver when switch 12 is closed. Well, what exactly does activate mean, right? Does that mean we want to apply full power for a fixed amount of time, a few milliseconds? Does that mean we want to apply partial power? What about if we wanted to apply partial power and then we wanted to hold that power on, not for a duration, but until the switch was released? Or what if we wanted to be fancy and we wanted to apply partial power and hold the power while we are not receiving a signal from a different switch? I know that one's kind of complex. Anyways, the idea here is that when we think about the automatic mode, or the whatever is going to happen when we tell a coil to activate, what we're talking about is its configuration. That's where we explain to the board, specifically we say, for this driver, this is how I want you to apply power whenever it's activated. So let's bring this back out of the world of abstract into something more concrete and talk about a pop bumper. When you think about a pop bumper from this I/O network perspective, all we're really talking about is one switch and one coil, right? So we've got the switch here. It's got that, weird spoon thing. And when the ball hits this white ring here, that depresses the spoon, which activates the switch. And then there's also a coil, which is this green label down here that will pull this part down and squish the ball out. So in the I/O world, a pop bumper is one switch and one coil. How we might want to set this up is we might want to say, well, when switch X, when this switch here, when it's closed, automatically apply 100% power for 20 milliseconds to driver Y, where driver Y would be connected to this coil. Now, one of the great things about this system is that because it's automatic, we're letting the fast network itself do the handling here. And so that means that we don't have to make a round trip. The fast board, because of this configuration, can detect when this switch is hit and very quickly activate this coil. Without this, what might have to happen, this isn't what happens, but without this, what would have to happen is the switch signal would have to go back to the computer. The software running on the computer would have to say, oh, this is for a pop bumper. And then the computer would have to send a command to the fast board to say, activate this coil. By using an automatic configuration, we get very snappy responses, and we have a game that feels snappy and fast. So going back to that example that I had described at the start, just to sort of recap how all of this comes together. The PC is connected to the Neutron over USB, but how do we actually send commands to it? Well, what happens is when that USB connection is plugged in, the Neutron will expose 3 virtual serial ports, one for each network. Remember, that would be the I/O network, the expansion bus, and the display bus. Instructions are sent by software over those virtual serial ports. And the way that we interact with the driver specifically is we can send an instruction or a command telling the I/O network how we want to configure a driver and whether we want to activate it automatically, manually, or disable it. So, all right, this is going to get slightly technical, but stay with me for a moment. So let's say we want to configure driver number 23, and we want to tell it to use mode 10, which is limited time power, that is, apply this much power for this duration. We want to tell it to apply power for 20 milliseconds, and we want to apply 100% power. All right, so one of the things that's a little weird, I'm not going to explain this, but in computer lingo, there's another number base called hexadecimal. And so, for example, port number 23 is represented as 17, 20 milliseconds is represented as 14, and 100% power, or 255, is represented as FF. So just hang with me for a moment. You can see here, this is the command that gets generated, so DL, so this is configure driver. You can see configure driver number 23, use mode 10, run it for 20 milliseconds, and 100% power. Ignore the rest of this stuff for now. Now, all that's doing is that's telling the I/O network that we want to configure this driver in this way. When it actually comes time to use that, we have to use a trigger. So that's what the T here is for, trigger. So here and again, you can see we're saying trigger driver number 23, which is 17 in hex, and do it manually. That's what 1 here is. If we wanted to tell it to run in automatic mode, that would be 0. What does that all build to?